There we go. And this really is something completely different. It's another textbook. For me, it was another class with a different professor. Dr. Rogers I had for linear systems. He was this wonderful Southern gentleman. Dan Shavar, he taught electronics, and actually took a graduate class from him as an undergrad in solid state lasers. He was a little offbeat. He came into class the first day of my electronics one's class and said, you know what my very favorite, this before he even introduced himself, you know what my very favorite thing is to do? I like to go in the bathroom alone at night and turn off all the lights and stand in front of the mirror with a roll of lifesavers and crunch them between my teeth. And then he just went on with the rest of the class. He also had some weird diode stories too, but we'll get to that. So by the end of the day, all lifesavers in the Auburn Electrical Engineering building were sold out. And we all went home and crunched lifesavers to figure out what was going on. That is your extra credit homework assignment, is to crunch some lifesavers. There's lifesavers available. It only works with peppermint or spearmint. I don't know why. Well, I do know why, but I'm not going to tell you. That's part of the assignment, is to tell me why they do what they do in the dark.
Does it have to be a lifesaver? Or can it be any sort of mint candy?
I don't know. I haven't actually tried it with Altoids, but I know it works with lifesavers. If you can't get lifesavers, you can always Google it.
Alrighty.
Okay, and there is a submission link and an assignment in BB Learn, believe it or not. This is Tem the Enchanter. I warned you this was a completely different course. You didn't believe me. For some of you, I can kind of tell you the pattern. Some people like that first two exams, what we've covered so far, the linear systems. They're the more mathy people. They're the people who like power systems and things like that, and maybe communications. The second half of the course, we're dealing with nonlinear circuits. And these are the people who are going to like microelectronics and my electives, and maybe Dr. Cambo's electives, and maybe Dr. Chen's electives, that kind of thing. Microelectronics, nanotechnology, those kinds of things. And there's a lot of work in Arizona in this field, and it's actually growing right now. TSMC is building a fab down on the northwest side of Phoenix. They're hiring 300 new grads this spring. And I don't know if there's 300 new grads in electrical engineering in Arizona, which means that if they're hiring, that means they're probably also hiring people from Intel. So Intel's hiring people, and they're hiring people from Microchip. So Microchip's hiring people. So it kind of like all bounces around, and on Semi and NXP and all those other places. So if you're interested in microelectronics, there's a lot of job opportunities here right now. We also have research opportunities in the lab. First thing I want to get straight, and this is the DJ memorial slide. Holes are real particles. They're not just from Bugs Bunny cartoons. We treat them like they exist. Well, they do exist. They're the absence of an electron, but they have an effective mass in the equations. In fact, they're heavier than electrons. And it's just the absence of an electron. I'll explain why they're heavier as we get more into this. But you have to treat the holes like they're real particles. If you don't, and this was the mistake all the original semiconductor physicists made, is when they were doing their calculations, they kept on getting all of their current answers were off by a factor of 2. They were half what they actually measured. and they couldn't figure out what was going on. And the reason why is there's an electron current going this way, which is negatively charged particles. At the same time, there's a hole current going this way, which is positively charged particles. Net effect is they algebraically add together and you get twice the current. So you really have to treat them like they're actual particles. This first part, we're going to look at diodes, and then we're going to delve into the semiconductor physics of diodes. It's kind of an introduction to the topic. And then we will go into MOSFETs, which are the building block of all integrated circuits, all microelectronics, nanoelectronics. They're dealing with MOSFETs. Those are the devices they're shrinking. This is a periodic table in case I have to refer to it at some point during the lecture. There, let me just write this down. I don't even have a marker out. What's wrong with me? Okay. Phosphorus is N-type. You understand why this confuses me. Phosphorus and arsenic. And boron is P-type. I'll forget that at some point. I'll just look at it. Okay. What we have when we're dealing with these semiconductors, they're mostly made with silicon. They do make them out of other materials, but we'll talk about that later. Silicon is right here. It's in group that it's in the group that has 4 valence electrons. And remember from chemistry, the magic number is 8. For stable compounds, we want to have 8 valence electrons in an atom. So what silicon does is it takes each of the 4 valence electrons and it covalently bonds 1 electron with its 4 nearest neighbors and forms a crystal. The first thing they do in semiconductor processing, and most of this is done in France for some reason, but they make, and a company down in Phoenix that is a subsidiary of a company in France, they make these really pure silicon crystals. They don't want to have, you know, they're down to like parts per quintillion of other atoms. Perfectly pure silicon. And this is what we're going to build all our devices on. Now, and it has kind of a mediocre conduction. Some of the places on this wafer, I'm going to want to put an N-type material. And if I want to have an N-type material, basically has an extra electron. So what I'm going to do is I'm going to bombard this perfectly pure silicon with things on the 5th column. It's usually phosphorus and arsenic gas, which is deadly. Stay away from it. That's another Dan Chavarism. In the tables of chemical properties for smells of different chemicals, the one for arsenic gas is blank. Because anyone who's ever gotten long enough to say, wait, it smells like almonds, is dead by the time they can get that out. Okay, really deadly. The building next door, JPL, when the alarms went off, I was told if the alarms are going off in the processing building, you just leave campus and go home. Drive as far away as you can, as quickly as you can. They were a little bit sloppy over there, the rocket scientists. Okay, so the stuff in column 5, if I bombard this pure silicon crystal with atoms at a high temperature and allow these atoms to infiltrate my crystal, things like phosphorus and arsenic are going to have an extra electron. So it's still, the silicon's going to be, it's not enough to damage the crystal. Silicon still wants to make 4 covalent bonds, but suddenly there's this extra electron hanging around and it's free to roam about the crystal and conduct electricity. Okay, this is called N-type. I felt the need to explain this before I got into the rest of my slides. Okay, if I take that same pure silicon crystal and I bombard it with something in this column, and it's usually boron, phosphorus and arsenic, I bombard it with boron. I've now put an atom in the crystal that only has 3 valence electrons. So it bonds with 3 of its nearest neighbors, and it leaves behind a hole. It's one place in the crystal where there is a positive net, there's an absence of an electron. And this absence of an electron can actually move through the crystal and conduct current, and that's hole. That's called a hole, and this is p-type. Okay, there we go. Nicholas Arnold. Okay, that's what I thought. I'll get you your exam after class. Okay. Okay, so we're moving into diodes. This is Cedra Smith, chapter 4.1 through 4.7. We're mostly going to cover chapter 4 and 5 and a little bit of 6. It's a really dense book. Yes, we do know the average on the exam, and I was going to write this down, so let's do this right now since somebody asked. Let's get the paper out. In fact, I put midterm grades into. Midterm grades are non-binding, and I don't do anything on as far as curving the averages other than just I round your grade up to a whole percentage point. So for exam 1, there were 7 A's, 8 B's, 9 C's, 3 D's, and 5 F's. And the average was a 78%, which is pretty good. That's in the ballpark where I'm not curving the exam grade. Overall, your overall class average, there's only 6 A's. There are 11 B's, 11 C's, 2 D's, and 2 F's. And most of the people who have D's and F's, I looked at them, that you're either in 1 or 2 positions. You have not turned in a lab this semester so far, or you had a really low exam grade. So you either need to start doing your labs, or you need to start studying more for the exams. As far as the grade breakdown goes, if this was final grades, I would probably play some games, drop a few grades here and there, and or curve the overall average so that I had a few more A's. So I might give you a point or two, like make an 89 or an 88 the threshold for an A. Is generally what I end up doing, but I don't curve grades for midterm grades. They'll disappear off your transcript. They'll never really go on your transcript. They're just to kind of let you know how you're doing in the class. Okay, diodes. Now we're getting, oh no, this is still over our slide. Now, the transistors, well, let's start with, okay. Yeah, keep the Cedra Smith book. It's like one of the few books that I ever had, college books that I referred back to, because it really delves down into the details and the theory of how they do the math to analyze these circuits. That'll help you if you're trying to optimize a circuit and you want to figure out, well, I want to make this a little bit faster. What things can I change that will make it faster, and not just shotgunning it where you're thinking, I'll try changing everything and see what happens. If I wanted to build circuits, I go to the Art of Electronics. That's a pretty useful one to have on your shelf too. And then I had some bunch of theory books, mainly because what I was doing at the time. So this is a really good reference book to have because it's like this thick. We're going to cover a total between 280 and 380. maybe about 5 chapters. And there's a lot more information in there you can use. I use some of the stuff that we skip, I do in 492. The way we build these is we take silicon and we deposit different layers of materials on them to form this structure where I have a source and a drain, and current flows from the drain to the source, electrical current, and the gate basically controls what the conductivity is in the channel between the drain and the source. It's a little bit complicated to get started with transistors. It's a 3-terminal device. Well, it's actually a 4-terminal device. There's a body too. We'll talk about that later. So they're a little bit complicated to talk about. The easiest thing to do is to start with diodes. But transistors, these MOSFET transistors, are what is it, except for maybe like 1 or 2 devices on the side. If you buy an Intel processor, it's pretty much all CMOS. It's all MOSFETs in one form or another. If you buy a Micron DRAM chip, it is MOSFETs and a bunch of capacitors. If you buy a flash, it's a weird MOSFET. But everything is pretty much built about MOSFETs, and this is what people think electrical engineers do. This is the first microprocessor. It's the Intel 4004. It was built in 1971. All these patterns that you're seeing on here, and there's a lot of repetition in here, are the different transistors arranged in different circuit patterns to pretty much build the different functions inside here. So maybe, you know, I've got like maybe some registers in here, I've got some memory in here, I've got an ALU somewhere in here, I can't tell you where it is. These are the bonding pads that actually connect to the outside world. Right here, let me see if I can find one. Oh, this right here is probably an ESD protection diode. And this is one of the biggest uses of diodes inside of integrated circuits, but they get used in a lot of power circuits too. It had, how many? I want to say it had like maybe 10,000 transistors on it, if that many. Now they have billions of transistors on them. So the basic idea behind these diodes is I take a P-type material and I grow it. First of all, I take my silicon crystal and I bombard it with N-type atoms like phosphorus. And then on top of that, I'm going to grow another region where I have more P-type atoms than N-type atoms. So it's going to become P-type. And I put them right next to each other, and there's this junction between them. So really inside, it looks more like this. Here's my, oh, sorry. I have an N-type substrate. No, I have a P-type substrate. Let's do this right. P-sub, and I put an N-well in there, an N-diffusion on top of that. And every place where these two meet, I have a p-n junction. It really looks more like that in the real world, but we kind of model it like this. This is my, well, I'll just go ahead and give it its right name. It's called the depletion region. Okay, and we'll talk about why we call it that in a minute. These are my slides. Now, the way these things work is current can flow from the P side to the N side. So if I put a positive voltage here and a negative voltage here, we get forward current, and it equals whatever current I need to maintain operation in the rest of the circuit. If I try to flip those around and put positive voltage on the N side and negative voltage on the P side, I get virtually zero current. It'll be femtoamps or picoamps. There'll be a little bit of leakage current, but not a whole lot. And hopefully today we should get through the physics of how this works today. Okay. Yes. Right. It's formed from a p-n junction. As far as naming the different sides, the p-type is called the anode. The n-type is called the cathode. And if you see it on a circuit diagram, a lot of time cathode is abbreviated as a K. And that's because the German word for cathode starts with a K. And it's just tradition at this point. Cathode ray tubes, they came from Germany originally. Now the circuit symbol, the N side looks like a minus sign. So that is the negative side. That's the easy way to remember that. Somebody, hold on. Yes, one side has extra electrons and the other side has holes. And there'll be more detailed pictures in a minute that I copied from an old textbook. Now, if you actually pull this device and it's not an LED out of a cabinet, there'll be a little stripe on it, and the stripe indicates that's the negative side. You can also do the little diode checker thing on it to figure out which side's which I usually end up doing. For LEDs, one of them has a longer lead and one of them has a flat side. And one of our junior technicians one time went into the parts storeroom and thought we got defective LEDs, and there was one leg longer than the other, and he actually went in there with a pair of diagonal cutters and cut all the leads the same length.
Oh no.
he never lived that down. Okay. So this is what's going on at the p-n junction. Now, the basic law we're going to deal with here is like charges repel each other and unlike charges attract each other. So in this N region, where I've got these free electrons zipping around, they're going to be attracted to the p side. And so some of them are going to zip over the junction and come over here. And likewise, the holes from the P region are going to be attracted to the N side, and they're going to want to zip this way. So the holes want to go that way, and the electrons want to go that way. All the electrons don't just migrate and make it charge neutral, because what happens as soon as an electron crosses this barrier over here, suddenly there's an overabundance of holes. And the electron finds a hole and it zips into it and it stays there and creates a neutral site. And it's a statistical thing. It takes a certain amount of, and it kind of looks like a length time constant. It takes a certain amount of length before pretty much all the electrons are recombined. And so there's this region in here where the electrons aren't combined. And being good semiconductor physicists and wanting all our field diagrams to look like squares, we just cut off a point in there and say, on this side, there's all electrons, and on this side, they've all recombined. And it's like the 67% point or wherever they decide to put it. So this region in between here is called the depletion region. And if you look at it, I've got positive charge on the N side and I've got negative charge on the P side. And anytime you have charge separated by a distance, I just got in this argument with Cole like 2 days ago, you have a capacitor. So, and a capacitor, whatever the laws of capacitance, Q equals CV. If I have a capacitor there, and I have charge separated by, I'm also gonna have a voltage. So it creates this barrier potential, VB, across the depletion region. You can actually measure it if you have a fairly high input impedance multimeter. The flukes we've discovered this week, do not have a high enough input impedance. If you put it in diode checker mode, it will measure the voltage across the diode. Say it's like 0.55 volts. But if you just put it in DC voltage mode, it doesn't have as high of an input resistance, and it measures 0. So just the current, the voltage dissipates through there. Yes, the anode is longer in an LED, I believe. I don't know that. I'm not a technician. What I do when I want to find that out, and I can never remember polarity and things like that, is when it becomes critical for me to know that, I have Google. I know one side's longer than the other and one side's flat. Okay. In case the technician goes and clips the leads on them. Right. So we got this depletion region in there. If I put forward bias across here, now I need to put a voltage across this diode that's greater than that barrier potential we saw in the last slide. I said when Coltwin measured the diode, he measured 0.55 volts. That's typical for a silicon diode. It's going to be somewhere between 0.5 and 0.8 volts. But again, sloppy approximations for engineers who are doing calculations in their head, we generally tend to use 0.7 of a volt for a silicon diode. That's good enough for hand calculations. If I want something more exact, I'll use the ideal diode equation and actually calculate VT and all that stuff, or look it up on the data sheet. If I put a positive voltage on the P side, so that's on the anode, I put a negative voltage on the N side, that little barrier potential that I have across that junction is overcome. It needs to be higher than the built-in, the barrier potential. So I put I make this greater than, it's DC. I make this greater than like 0.7 volts DC. And I take this end and I ground it. If I do this, I have enough voltage to overcome that barrier potential and current just flows freely through it. And we'll get to that slide today. It will, in theory, conduct as much current as your circuit allows it to. So really important when you're using a diode in a circuit, you want to have something in that circuit that limits the current, like a resistor. This is why all those LED circuits you see have that little resistor on there. It limits the current and keeps you from destroying the diode. Back at my old school, I had this one kid, he did not put the limiting resistor in there. I saw him, he had like alligator clamps from the positive 5 volts and alligator clamp to the negative to the ground, and he just connected it right across the diode. And I looked down and I saw it. It was the most amazing yellow I've ever seen in my life for about a split second, and then it just went poof. It conducted way too much current. So that's what those are for, and we'll get to things like that. If I put it in reverse bias, what happens is that depletion region actually gets to be wider. So you're making the barrier height, whatever reverse voltage you put across there, adds to the voltage across the barrier, and it makes it harder to conduct. And virtually no electrons get through. Oh, this is such a relief. I'm not teaching math. And Dr. Ferry's going to come and talk on Thursday. What more could be better? Okay. So when I'm in the lab and it's late at night, and I'm trying to figure out, is this circuit working or not? This is the most basic model of a diode I can put in there. If I have positive voltage on the P side and negative voltage wait, that's okay. I put positive voltage on the P side. I put negative voltage on the N side. I just model the diode as a 0.7 of a volt battery. And we'll do a lot of this. It's like a binary logic circuit. Is the voltage greater than 0.7? Then I stick a battery in there. Is the voltage less than 0.7? Then I stick an open circuit in there. And if you have an AC signal going in, you have two different models based upon where the voltage is. And this is the IV characteristic. If the voltage across the diode is anything less than the built-in potential, about 0.7 of a volt, I have zero current. This is my current axis, and this is my voltage axis. And if I put a forward voltage of 0.7 of a volt, I get whatever current I need. Notice it doesn't really like, this curve doesn't model 2 volts. We'll look at what happens when we get to 2 volts a little bit later. It involves smoke and flames. Okay, so basic circuit models, we've got one-way current flow. It's either a short with a voltage drop, or it's an open. A more exact model is used by the ideal diode equation, which is a better equation. And yes, there's even more complicated equations like that in C's book. A diode is, yes, there is leakage current before the built-in voltage limit, and it's actually kind of exponential. Well, it is exponential in that region. And we'll look at numbers in the equation in a little bit, what those numbers actually are when we get to the ideal diode equation. Oh, okay, we gotta do this thing first. Don't panic, it's a transformer. I taught 188, just, it's okay. I'm not gonna do the dot thing on you. All this transformer does, and you can use this from now on. AC line voltage is 120 volts. It reduce, in this case, it's going to reduce the voltage. So over here, I have 12 volts. Where did it go? It reduces the voltage, increases the current by the same amount through the magic of transformers. Now, this is 12 volts AC. So there's two conditions I have here. Since it's an AC, oh, it says it's 10 volts. So we're going to make it 10 volts. It's a different transformer. 10 cosine omega t. In the positive half of the cycle, I'm going to have, so this is the positive half. We'll do this in black. I'm going to have current flowing through this diode, but it can't flow through D4. And then it's going to have to go through the resistor, and then it will flow through D2. So current flows through this path. Okay, see if I can get away with this semester. In the negative half, see if my chat's lighting up. I am going to have, so this is, in the negative half, this is the positive side. This becomes positive relative to here, because this voltage, as I've got it labeled, is negative. So current will flow through D3, through the resistor, and back through D4 and return. Since I've changed, I got somebody complaining. Since I changed the polarity of the voltage, it's going to come out positive both sides. Let's see what you said. Is this a Wheatstone bridge? It's like okay, it's sort of like a Wheatstone bridge, but Wheatstone bridges are usually associated with resistors. It's the same kind of topology, but this is called a full wave rectifier when we put diodes in there. Okay. You should have seen the look on my face when I realized I had to teach 188 for the first time. And we got to the part on Wheatstone bridges. Like, I never understood this. Okay, so basically what we have here is we have in the positive part of the cycle, let's do the positive part of the cycle first. So I've got a sine wave that looks like this. They all kind of look like that when I draw them. And in the positive part of the cycle, what I'm seeing is I'm seeing this black line here, 2 diodes and a resistor. So the voltage across the resistor is going to be 2 diode drops less. So it's going to be kind of like this. If this is 10, this is 10 minus 1.4 is 8.6. And that's in volts. Okay. And those diodes do not conduct at all. But when I get back to the positive part of the cycle, oh, great, I froze. Okay, I will be back shortly. We're on slide 15. We'll get to